Woodpeckers in Lima's study were able to calculate habitat payoff by sampling resources in different patches. Sampling allows animals to update information on resource content in different patches, helping them to decide where, as well as when, to move. In other words, animals must divide their time between remaining in the most profitable patch and sampling nearby patches so that they can keep track of current levels of resources. In the lab, great tits balance sampling and foraging behaviors based on the difference between rich and poor quality patches. As this difference increases, birds spend less time sampling and more time foraging in the most profitable patch. This makes sense in that it is easy to determine which patch is the best if there is a large difference between them. Both great and blue tits display the same pattern in the natural environment, foraging primarily in resource-rich patches, but taking time out to sample nearby patches. Indeed, the foraging sampling division of time is such that birds taking food back to their nest come close to the maximum possible rate of prey delivery in each patch. Foraging patterns of many other animals fit the marginal value theorem, at least on a general level. When deviations occur, it is usually because animals stay in a patch after resources fall below the marginal value. This could reflect the fact that moving to a new patch introduces unknown risks, such as predation. Moreover, other behaviors, such as searching for mates, compete with foraging, so it can be difficult to determine why animals do or do not move to a new location. Some researchers point out that these challenges, i.e., identifying all of the factors that impact foraging, minimize the utility of any optimality theory. Even so, marginal value theory provides a good starting point for understanding decision-making during foraging. Ideal free distribution model. Marginal value theorem explains foraging behavior at the level of the individual, but many species forage in groups. Under these conditions, the payoff in a resource-rich patch is lower if most of the animals congregate at this location. Rather than staying in the highest payoff patch, therefore, a better strategy is for animals to distribute themselves among patches. The ideal free distribution model takes this into account, proposing that the number of animals aggregating in a particular food patch is proportional to the amount of resources available at that patch. Early support for this model came from an experiment with three-spined stickleback fish, in which food was dropped into either end of the aquarium at different rates. Sticklebacks distributed themselves accordingly. If twice as much food was dropped at one end, twice as many fish aggregated at this location. See Figure 7.4. Animals took time to sample resources at both patches before they split into these groups. Individual animals continued to sample the other patch periodically, allowing them to update information about the rate of food delivery at both locations. Foraging bumblebees also conform to an ideal free distribution model, in that they distribute themselves based on the density of flowers and the concentration of nectar in each plant. Ideal free distribution is difficult to assess in humans, but one could imagine that a group of apple pickers would distribute themselves so that there are more individuals at the trees with the most apples. Moreover, people playing a competitive game in the lab selected colors that were associated with different payoffs by taking the choices of other players into account. The general pattern of decision-making across the group fit the ideal free distribution model, even when the payoffs changed across trials. Figure 7.4. Ideal free distribution model in stickleback fish. Food was dropped into each end of an aquarium, patches A and B, and the number of fish aggregating at each location was recorded. The arrow indicates the beginning of food delivery. When no food was available, fish were distributed randomly throughout the aquarium, bottom left, when food was delivered at a rate of 5-1 in patch B versus patch A. Fewer fish aggregated at patch A, bottom right. Okay, so we have a line graph. The y-axis is percent of fish at A from 0 to 60, and the x-axis is time in minutes from 0 to 15 minutes. Okay, so at about 3 minutes, food presentation occurs, and that corresponds to a peak of the greatest number of fishes at A, and then that drops off after the food presentation. Okay, so in the bottom left picture, you can see that the fish are just all over the tank. There's no pattern because there's no food going on. And on the bottom right, you can see that there's about a 5-to-1 ratio of fish, 5 times more fish on the left end of the tank where 5 times more food is being distributed, and then there's about a fifth of that at the right hand edge of the tank at B because a lot less food is being delivered there. Group foraging by many other species often fits the ideal free distribution model. Exceptions occur most commonly when there are more individuals at the least profitable patch than the model predicts. Harper in 1982 explained this discrepancy in an experiment in which researchers threw cubes of bread into opposite sides of a pond full of mallard ducks. Ducks distributed themselves, approximately, according to the rate of food delivery at each site. Variability from this ideal value was due to a few dominant birds that monopolized most of the resources at the more profitable patch. This competitive advantage of higher-ranked individuals also explains deviations from the ideal free distribution model in foraging long goldfish and coho salmon. Under these conditions, dominant animals have greater access to food resources, further perpetuating their competitive advantage over other group members. Social foraging that does not fit an ideal free distribution model could also reflect differences in sensory and cognitive capacities. For example, cichlid fish that consume less food than conspecifics often spend more time sampling other patches, perhaps reflecting an inability to discriminate resource content at different sites. Finally, many researchers have noted that foraging groups may not distribute themselves according to an ideal free distribution because the model makes assumptions that are not always met in the natural environment. First, individuals are not always free to move to a new location. Dominant individuals, social restrictions, e.g. caring for young, or physical constraints may limit travel between food sources. Second, unlike Harper's experiment in which bread cubes were replenished continuously, resource content in a single patch is not stable. This has an obvious impact on an animal's decision to move to a new patch. Despite these limitations, the ideal free distribution model provides a general description of how individuals within a group distribute themselves during foraging. The model makes an important contribution to optimality theories by highlighting how social interactions impact choice behavior. The general idea that group decision-making is an interactive process in which the optimal strategy for one individual takes into account the choices of other individuals is formalized in the Nash equilibrium. See Box 7.2. Box 7.2, the Nash equilibrium. The Nash equilibrium is named in honor of the U.S. mathematician John Forbes Nash, born 1928, who won a Nobel Prize in economics for his work on the forces that govern group dynamics. Nash's life, particularly his struggle with mental illness, is profiled in the 2001 film A Beautiful Mind, loosely based on the book by Sylvia Nasar, 1998. Although many biographical details are fictitious, the film provides an accurate, although simplified, description of Nash's theories. In the film, Nash comes up with the idea of advantageous group choice when he and his graduate student friends at Princeton discuss how to approach a group of women in a bar. In contrast to the standard each man for himself tactic, Nash proposes that they all have a better chance of success if they work together. It is unlikely that this incident was the origin of Nash's theory, but it is true, as the film relates, that he was offered a position at MIT based on the strength of his theory describing group dynamics. According to Nash, decision-making of individuals in a group cannot be understood in isolation. Rather, the choices of each individual can be predicted only when the decisions of others within the group are taken into account. A premise of this idea is that all individuals know the strategy or decision of others. Group decision-making has reached a Nash equilibrium if no single individual in the group can improve their payoff by unilaterally changing their strategy. The mathematical formulation of the Nash equilibrium provides a solution for these situations in which there is no advantage to changing strategies, given that the other players remain consistent in their own actions. The Nash equilibrium can be understood in terms of Harper's Cambridge pond experiment with ducks. If ducks distribute themselves in a way that matches the rate of bread delivery, any subsequent movement between patches could only be disadvantageous to that individual. Specifically, if 30 ducks were in a pond with one researcher throwing in one bread ball every 10 seconds and another throwing one bread ball every 20 seconds, ducks should distribute themselves so that there are 20 at the first site and 10 at the second. The amazing thing about Harper's experiment is how quickly the ducks sorted themselves into an equilibrium. Even after 90 seconds, when fewer than 10 pieces of bread had been tossed into one end of the pond or the other, ducks redistributed themselves according to the Nash equilibrium, or ideal free distribution model. During this time, many of the ducks had not even sampled one of the bread cubes. Moreover, even though individual animals moved unpredictably, the group maintained an equilibrium. The Nash equilibrium has been used to analyze strategic decision-making in competitive situations, ranging from war to professional soccer. It may also describe the outcome of cooperative efforts, such as those related to educational attainment. Group dynamics of cooperative behaviors will be discussed at length in Chapter 11 under the broader category of game theory, also one of Nash's major theoretical contributions. Collective decision-making. The impact of social interactions on choice behavior is particularly striking during collective decision-making when large groups of conspecifics engage in coordinated activities such as foraging, nest building, or migration. Even though each group member only has access to a portion of the information needed to guide behavior, direct or indirect interactions between individuals lead to group cohesion. These group behaviors, which seem to be independent of individual actions, include swarming bands of locusts, migrating flocks of birds, and marching colonies of ants, see Figure 7.5. Even crowds at large sporting events or concerts appear to behave as an organized unit. Collective decision-making, also described as evolved coordinated behavior, provides a fitness advantage to group members in that they benefit from the consequences of synchronized group activities, despite individual preferences or differences in the ability to access or process information. Figure 7.5, large-scale coordinated behavior displayed by milling fish. So it's so cool. They're all swimming in like a spiral. Like it's a beautiful piece of art, all synchronized. Large-scale coordinated movements that emerge from collective decision-making appear to be regular and predictable, suggesting that these cross-species behaviors are governed by general principles. One of the most important is that collective decisions are robust to individual perturbations, and that a single defector will not alter the overall behavior of the group. For example, stickleback fish largely ignore movement of one neighbor, but once a critical mass, quorum, moves in a particular direction, all individuals in the group follow suit. Moreover, increasing group size increases the accuracy of collective decisions, suggesting that this process may be more effective and efficient than individual choice. Similarly, the larger the group, the fewer individuals are needed to lead a behavioral choice. Leadership is not a prerequisite for coordinated group activity, but when it occurs, leaders are usually informed individuals who have access to pertinent and salient information. In the case of migration, these individuals have experience traveling along the navigation route, although there are many experienced individuals who do not act as leaders. At least with humbug damselfish, leadership in swimming direction is not related to social dominance, so it is not clear how leadership is determined in these collective decisions. In some cases, potential leaders, i.e. informed group members, reach a consensus decision that depends on the degree of disagreement between them. For example, When homing pigeons are released in pairs, they take a route partway between their trained routes when they are relatively close together, but select one route or the other if the distance between the two is great. The movement of human crowds follows the same general pattern. Recently, the processes underlying collective decision-making have been examined within the framework of cognitive neuroscience. According to this model, the behavior of neural networks mimics those of ants working together to carry out essential tasks such as nest building or foraging. In both cases, individual units, neurons or ants, exhibit a low propensity to become spontaneously active, which is modified by encounters with local, discrete stimuli, electrical or chemical signals for a neuron and pheromone signals for an ant. This leads to low levels of excitement, intracellular changes or ant movement, and, once a threshold is reached, the ant or neuron changes from an inactive to an active state. This excitement spreads to adjacent units, such that amplification of activity occurs rapidly. Both ants and neurons display an inactive period following activity, refractory period, during which there is a low probability of switching into an active state. In other words, both neural networks and ant colonies display synchronous patterns of activity, even though the individual units are not intrinsically rhythmic. Neuronal networks are an efficient way for the brain to elevate activity close to threshold, providing discrete windows of high responsiveness to external stimuli. In the same way, synchrony among ant colonies functions to efficiently allocate workers to required tasks when sensory cues are detected by individual insects. It is unlikely that this model will apply to all instances of collective decision-making, but it is a thought-provoking attempt to explain how interactions among individuals scale to collective behavior with its own functional properties. It is important to note that collective decision-making is distinct from cooperation, when two or more individuals work together for a common goal. Cooperative behaviors have an immediate gain for all actors, which is not necessarily true with collective decision-making. Moreover, defection has no negative consequence in collective behaviors, but it is clearly disadvantageous in cooperation because actors gain by working together. For these reasons, group behavior of social insects appears to fit the definition of collective decision-making rather than cooperation. Of course, this is not the final word on the topic. Many researchers are convinced that these tiny organisms cooperate with conspecifics in a way that differs very little from other animals, including humans. Beyond foraging. Most of the discussion in this section relates to foraging, but the same decision-making processes can be applied to other naturalistic behaviors, such as aggression, when and what to attack, habitat selection, when and where to move, or reproduction, whom to mate with and when. A simple rule of the lowest energy expenditure for the highest fitness benefit provides a general explanation of how decision-making occurs in these situations. These decisions are affected by cognitive processes, including memory, timing, and discrimination. For example, if animals move to a new foraging patch based on a marginal value, they must be able to calculate how resources in the current patch are changing, estimate the travel time to the next patch, and remember the quality of other patches in the habitat. Constraints such as travel costs, potential predation, and current metabolic state of the individual also affect decision-making, such that a particular choice may appear less than optimal at the moment, but results in reproductive or survival advantages in the long term. In sum, optimality theories all contain three components: a choice behavior, a currency that allows the costs and benefits to be compared, and cognitive and environmental constraints that alter the relationship between these two. All three of the optimality theories discussed in this section, optimal foraging, marginal value theorem, and ideal free distribution, assume that natural selection has shaped choice behaviors associated with foraging and other naturalistic behaviors. Although behavioral traits associated with these activities may be heritable, It is not a specific motor response, e.g., breaking open a shell to retrieve a mussel, that defines decision making, but the rules by which animals make these choices. Moreover, it is not a particular choice that is inherited, e.g., select intermediate-sized mussels, but the cognitive process that leads to this decision, e.g., calculate foraging payoff given the relative abundance of different-sized mussels. In this way, animals can adapt their choices to changing environmental conditions so that they behave efficiently in a variety of situations. Choice in the lab. As with research in the natural environment, there is a long tradition of laboratory work examining decision-making in different animals. Most scientists working in this field are psychologists, who examine how pigeons or rats respond in operant paradigms that involve a choice. While not ignoring functional explanations, these studies focus on proximate mechanisms of decision-making by investigating factors, e.g., biological, environmental, or motivational, that influence the selection of one behavioral option over another. The matching law. Choice experiments are set up in the lab using concurrent schedules of reinforcement, i.e., those in which two or more schedules are in effect simultaneously. Using pigeons as an example, if pecking one key produces food under a fixed ratio, FR5 schedule, and pecking another key produces food under an FR2 schedule, 2 versus 5 responses produce a food pellet. Pigeons respond almost exclusively to the FR2 key. The situation becomes more complicated when an all-or-none strategy does not produce the best payoff. This may occur if the two keys are reinforced under different interval schedules. FI 30 seconds and FI 45 second schedules would mean that pecking one key produces a reward after 30 seconds and pecking the other after 45 seconds. Because the intervals associated with each key continue to progress even when animals are not responding, pigeons receive the most rewards if they move back and forth between the two keys. See Figure 7.6. This is exactly what they do. Figure 7.6. Design of a concurrent choice experiment in pigeons. Birds have the choice between two operant responses, left and right key peck, that deliver food rewards under different schedules of reinforcement. So we have a very dapper looking pigeon looking at the two keys. Okay. So one is a VI 60 seconds, and the payoff is about a minute, and one is VI 20 seconds, the payoff is about 3 a minute, so they will peck the 3 a minute option almost exclusively. Concurrent schedules of reinforcement may be set up in a variety of ways using interval or ratio schedules with either fixed or variable parameters. Most commonly, these are designed so that the maximal payoff occurs when animals divide their time between two or more behavioral options. The matching law explains how this division occurs by stating that the relative rate of responding on one alternative matches the relative rate of reinforcement for that alternative. This can be written as a mathematical equation in which B equals behavior, R equals reinforcement rate, and sub A and sub B refer to two behavioral options, e.g. two different levers. Okay, so B sub A divided by B sub A plus B sub B equals R sub A divided by R sub A plus R sub B. Okay, so this would translate in words to, choice A divided by choice A plus choice B equals the reinforcement rate of A divided by the reinforcement rate of A plus the reinforcement rate of B. Choice behavior that fits the matching law has been observed in a variety of species under a number of different experimental conditions. The matching law also explains choice behavior when responding for each alternative requires a different amount of effort, when rewards vary in quality or quantity, and when there is a delay between the response and the reinforcer. In most cases, animals divide their responses in such a way that they maximize overall gains across sessions. When choice behavior deviates from the matching law, It usually does so in one of three predictable ways. Some animals exhibit a bias for one alternative or the other, regardless of the reinforcement payoff. For example, an individual rat may prefer to respond on the left rather than the right lever, or a pigeon may prefer to peck red rather than green lights. If identified, this confound can sometimes be eliminated by restricting access to the biased alternative during training. Most commonly, animals exhibit undermatching, in which they appear less sensitive to reinforcement rates than the matching law predicts. In essence, subjects respond at higher rates on the lower payoff alternative than expected. Overmatching describes the opposite pattern. Animals appear more sensitive to reinforcement schedules in that they respond at higher rates on the higher payoff alternative than expected. It is not clear why animals have a tendency to undermatch, but it likely reflects the specifics of a lab environment. Unlike the natural world, food is constantly replenished in most operant choice experiments. In addition, the two response options are close together, levers or keys on the same wall of a chamber, so animals can readily switch back and forth between them. This contrasts with movement between patches in the natural environment that takes both time and energy, not to mention the possibility of predation. The costs associated with moving to a new patch can be simulated in the lab using a changeover delay. Switching from one response option to the other delays the presentation of the next reinforcer. Under these conditions, undermatching is minimized and, in some cases, overmatching emerges. Overmatching resembles the scenario described in section 7.1.2, in which animals stay longer in a patch than predicted by the payoff provided by that patch, i.e., beyond the marginal value. Undermatching may also reflect sampling that occurs in the natural environment when animals test reinforcement payoffs in different patches. This may explain why undermatching declines with increased training. Animals do not need to sample as frequently when they have more experience with the payoffs provided by each alternative. The matching law has been applied to human behaviors as a way to explain how people direct their conversation to different individuals, how professional athletes choose one sports play over another, how consumers make choices between food items, and how children divide their time among activities in a classroom. Although these data are not as straightforward as those generated by concurrent choice experiments in the lab, they support the idea that humans, like many animals, possess the capacity to compute relative reinforcement payoffs and to adjust their behavior accordingly.